Good evening, everyone. We have a special event tonight regarding the cold fusion revolution. My name is Tom Vallone. I'm president of Integrity Research Institute. And we have a half-hour seminar by Dr. Martin Fleischmann on the history of cold fusion with past, present, and future. And with us tonight to give the introduction is Dr. Scott Chubb from the Naval Research Lab, who's here on his own time. Dr. Scott.
Yes, this has been a very contentious area. The scientific mainstream science has really broken down with regard to discussing this issue. There's been remarkable progress during the last 10 years. It does turn out, for example, that there's substantive scientific evidence that room temperature nuclear reactions do occur without accompanying high energy particles. And much of the confusion seems to have reflected this fact. In particular, it's been found that helium-3 and helium-4 seem to be the dominant particles, and people didn't recognize that fact at the beginning. And much of the contentiousness came about because of that. People do make mistakes, though, and I think it's time to rectify the situation. The Naval Research Laboratory was involved with this area at an early point. But it became so contentious that they really can't be involved in a mainstream fashion now. However, we still do listen to what goes on, and it was a fortunate consequence of that fact that we have maintained significant contact with people like Martin Fleischmann, who is the co-discoverer of cold fusion with Stanley Pons. And in fact, he has recently visited the Naval Research Laboratory and given a very important lecture on this subject. Dr. Fleischmann, of course, was a professor at Southampton University. He is a fellow of the Royal Society. He has done numerous things. He is very much viewed as an extraordinary scientist with extraordinary wisdom about directions in science. It is really very much a pleasure to introduce him. I'm sorry to give such a long introduction, but without further ado, here's Professor Fleischmann.
Well, I'm very glad to be with you here tonight. I've had a number of talks in the United States, and I think that the bias of what I'm going to say tonight is somewhat a reflection of what I said in the other talks, an abbreviated reflection of what I said in the other talks. But I think some of the points I'm going to make tonight do have to be made to correct some of the impressions which have been given by other people of this research field. Now, it is always said that a historical perspective on a subject is a bad idea, that you should never lecture in a historical context. But I think that's a mistake. It is sometimes well worthwhile to say something about the history of the subject, because that history points really where we came from, that is the past, and then in turn points to the future. So let me just tell you that I started to think about this subject at the end of 1947 when I ran across some extremely interesting papers by a scientist called Alfred Coehn, who was working in the University of Göttingen. And what Alfred Coehn found was that if he took a zigzag of palladium wire and charged it at one point, say the middle of this wire, and then applied an electric field to the wire, say this is positive and this is negative, he found that hydrogen moved more quickly to the negative end of the wire than to the positive end, and if he allowed this movement to take place, then after some time he could reverse the sign of the polarity, making this negative and this positive, and the hydrogen would move back again. Now that was really a remarkable observation, because it showed when it was evaluated, this experiment was evaluated scientifically, that hydrogen. Okay. Okay. Yeah. Okay.
You can move over there.
Yeah. Okay. I think I shall have to move this, because I shall fall over it. That's okay, Scott. Shall I start from the beginning again? Yeah. That hydrogen moved more quickly to the negative end of the wire than to the positive end, and if after some time the polarity was reversed, so this was negative and this was positive, the hydrogen would move back again. Now, what was interesting about this was that when this experiment was evaluated quantitatively, it showed that hydrogen in this lattice of palladium was present just as protons. That's the smallest possible species of charge, the positively charged species. And of course, this was done with hydrogen because deuterium had not been discovered at that time. It came later in the 1930s. Now, what was remarkable about this was that the hydrogen was mobile in the wire. At the same time, hydrogen had to be extremely strongly bound in the wire. And these two observations are contradictory if you view them in a simple-minded way. It showed that there had to be a rather complex interaction of the species in the wire. And the question which I posed myself at that time was whether one could use this change in the energy, it's really the potential energy of the species in the lattice, to compensate for the kinetic energy, so that one would be able to achieve the conditions which would allow fusion if one used deuterium. Now, at that time, I decided that this was not possible for a variety of reasons, mainly because of the knowledge of quantum mechanics at that time indicated that this would not be possible. Now, at a much later date, in the 1960s, I came to realize that charged species in liquids, and of course, in a sense, the proton or the deuteron in the lattice is a charged species in the lattice, are treated in the conventional sense. The scientific interpretation is based on a static species in the lattice, and we know, of course, that this cannot be because the species is mobile. As I've just told you, the species itself moves in the wire. And in fact, the species undergoes a random, thank you, the species undergoes a random motion in the wire. And when one considered this, when I considered this, I realized that really there was a very large class of research topics which could be built on the question of treating the motion of the particles in taking into account the motion of the particles and not regarding the particles as being frozen in the lattice. And the formalism which is used for that is quantum electrodynamics. And I should perhaps just say, perhaps Dr. Chubb can expound on this in summarizing the lecture, that we have been, as you know, initially we had just a nothing theory of nature. Then we had the progression through Galileo and Newton towards classical mechanics. Then at the beginning of the century, we had a shift towards quantum mechanics. And in the second half of the century, we should have got to the point of analyzing these types of problems with quantum electrodynamics, which is shall we say, a more complicated version of quantum mechanics. So at that time, we asked ourselves, I asked myself the question whether or not we could set up a series of experiments. This represents the random motion of the ions, where we put the question of the paradigm ahead of the experiment design. Now, normally when we do a scientific experiment, we don't bother about this. We just say, let us go into the laboratory and do an experiment and get some results and interpret them. But this is not true, because every experiment we do is based on a paradigm, or really it is based on a model which is based on a paradigm. So if we make a more exact, interpret this in a more exact way, we would have to say that we look at the paradigm and that it can be either classical mechanics or quantum mechanics. Now, when we do this, we find that very often the interpretation is not sensible. And what happens then in science, in general in science, is that the paradigm or its model is changed. There's a shift, a modification of the paradigm. And everybody, the majority of scientists are quite happy with that type of structure. Whereas, of course, what we should really say, that when we don't get a satisfactory interpretation, we should say, well, what would happen if we scrap this approach and instead put another paradigm at the center of our investigation? So let me just hide the bottom part. And in this particular case, we'd say we'd have to put quantum electrodynamics at the center of the center stage. Now, the problem with this approach was it was very difficult. I had about 17 research projects, of which I investigated 4. And you could never see that you would get a clear-cut demonstration of the need to introduce quantum electrodynamics into this picture. And then as I got older, I got more impatient, and I said, well, what we really need to do is to investigate a system where we must put quantum electrodynamics center stage, then design an experiment, forget this thing at the bottom at the moment, which gives us a result. We design the experiment, which gives us a result, and the interpretation is satisfactory. And this happened to be the cold fusion experiment. Now, I really didn't want to say anything about this experiment. I just wanted to satisfy myself intellectually that this was correct, because I really wanted to go back to these experiments. Having established that it was necessary to do so, I wanted to go back here. But unfortunately, this material became public on March the 23rd, 1989, and we became absolutely trapped by this lower half of this view graph. I think that's really all one. I think I should also say that there is now one other system which would fulfill the same need. I know of one other system which, if the experiments are correct, would only be interpretable in terms of quantum electrodynamics. And of course, if you think of the future of the subject, it might be much more sensible to cast around and find other illustrations of the need to involve quantum electrodynamics in the modeling, in the interpretation and modeling of liquids and solids, because if that ever became the accepted pattern of the accepted view, then cold fusion would be seen to be an entirely logical consequence. However, that has not happened yet. Now, at a somewhat later date, this was still not sufficient for us to engage in the topic of the possibility of finding nuclear reactions in at low temperature. But at a later date, from another investigation, I came to the conclusion that really, if these are the deuterons in a lattice, you really had to model a lattice containing deuterons as being a very large quantum system. And that being so, of course, one would come to the conclusion that the reactions of deuterons to the fusion of deuterons would be much faster in this type of lattice than they would be in plasma. Now, a plasma is a very hot collection of deuterons where you are considering the collision of deuterons in a very dilute gas, and it is normally considered that you have to achieve these conditions to get the fusion of deuterons. But this opened the door, in a way, a chink in the door towards investigating the reactions of deuterons in a lattice. So the question which we asked ourselves was, would the nuclear reactions of deuterons, D+, compressed into a host lattice be different to the reactions of D+ in a plasma? That was one question. And the second question is, could such effects be observed? Now, I think it's very important to specify the question at the outset, because if one asks a senseless question which has no answer, then you just get an ambiguous experiment. But if you can specify a simple set of questions, you have some hope of coming to some conclusion about this. I think there was evidence. I should say that the fusion of deuterons was discovered in 1934 by Oliphant, Hartek, and Rutherford. And there was already evidence right at the beginning that there was something very strange about what is called hot fusion. Our picture of hot fusion was not complete. And if people have questions about this, I think we can go into this later. And the way we decided to investigate this is to, these are the systems which we consider the possible ways of implementing this particular type of investigation. Let's just look at the first two. Our favored methodology at that time, right at the beginning, was to use, I knew I saved it, our favored methodology was to use precise, thank you. Our favored methodology was to use this technique of moving deuterons along a wire in order to achieve a very high concentration at the negative end. But for a complex set of reasons, we did not do that. We, in fact, took the system, the second system on our list. We charged a palladium electrode in heavy water with deuterons in order to see whether we could find any evidence of their fusion. And as I'm sure most people know, we chose to do this by measuring the heat released. So we used a palladium cathode surrounded by an inert anode in an electrolyte in heavy water. The rest of it is really fairly obvious. What you do in here, you have a temperature sensor and a heater to allow you to calibrate the system. Now, the results we got, I think it's very important to emphasize that when you devise an experiment of this kind, you should, of course, see whether or not the system works in a satisfactory way. is this a sensible design of equipment for investigating such effects? And the way you do this is to take a system which you expect has no effect. And one of these, a system which you would expect to have no such effect would be one in which you replace the palladium electrode with a platinum electrode, an inert electrode. You leave everything else the same. I think this is called a blank experiment. The blank experiment should mimic as closely as possible the experiment which you wish to carry out. So I think I just show you that, I think I should show you what the evidence was. It's historically interesting. Yes. A blank electrode shows an entirely sensible behavior. This blue line is the temperature time curve. The red line is the voltage you apply to the cell. And what you see is entirely reasonable behavior. The temperature comes to an equilibrium position here. If you then apply a heater calibration to the system, the temperature increases. If you take the calibration heater off, it relaxes. And I think the very important point you can make is that this relaxation after applying the heater pulse is flat. It relaxes to a constant point. If you take the heater pulse off, it relaxes back to the baseline. But the scientific way you investigate that is to say, well, what is the actual heat released? And if the system is behaving properly, and unfortunately this doesn't really quite fit onto the view graph, you find that the expected behavior, this is what is called in science a normal distribution. The errors are normally distributed. And the mean here, the mean excess heat in such an experiment is, I think it is here, 79 microwatts, whereas you are putting in about 2 watts. So within about 1 part in 10 to the 4, there is no excess heat. The other way scientists look at this is to say, what is the deviation, the standard deviation? What is the sort of width of this curve? And that here is, if you note that there, here is about 6 milliwatts. Now, the reason why this is so important is that if you now look at the heat release if you now substitute a palladium cathode in here and look at the heat release, then you find an interesting pattern of behavior. You initially see excess heat produced. That is because putting deuterium into the lattice releases heat. And then when the lattice is fully charged, you expect this to go to 0. But it doesn't. It builds back up again. And I think you can see that this is the excess heat released. This scale here, you can see this is about given by the deviation, the standard deviation of the experiments. But there is not much, there's no real doubt that you can see the excess heat released. Now, I think what is so important about this is you have to ask yourself right at the beginning, why did people find it so difficult to detect this process? Well, the answer is they did not do the experiment in a way which would give them mean 0 and a low spread in their measurement. If you do your measurement without having the required accuracy, then of course you will not see this. This will be buried, the noise will be so big you can't detect it. Now, I think historically I should also tell you that by March 1989, we had seen, this slide takes us to October 1999. By March 1989, we had seen heat release of the order 20 watts per cubic centimeter. for the electrodes, which is about what you would get in a gas-cooled fission reactor. And then we got into a great deal of difficulty about this experiment, and we did several more experiment cycles to convince ourselves, and possibly other people as well, that what we had done was sensible. And by October 1989, we'd got to about 100 watts per cubic centimeter. Now that slide here, this is a logarithm of the excess specific energy. That's the energy per cubic centimeter, or if you had a bigger system, it would be the excess energy per liter or something. And you see this 2 here means that you have 100, this is 100, and within the accessible range, we got to about 100 watts per cubic centimeter, which is certainly comparable to what you can achieve in a pressurized water reactor. So come October 9, my colleague Stan Pons and I had seriously considered at various times that we should terminate this research, but come October 1989, we'd got to a point where we felt that we really should carry on and see how much further we could get. Now, I think it might be appropriate here to say what you will really have to do, to put a sociological perspective onto this right at the beginning. People talk a great deal about finding alternative sources of energy, but of course, these sources of energy have to compete with the existing technology, and our existing technology is based on combustors, just burning something, burning a fuel. And the combustor is just about the cheapest form of chemical reactor you can devise. It's the cheapest system you can devise. So not surprisingly, wind power, wave power, any power you can think of turns out to be uneconomic compared to a combustor. This type of system is very strange. It has although it has a significant capital cost, it is not the anticipated capital cost is not really very high, but it is of course high compared to a combustor. But the cost of the fuel is very low. Now, if you want to generate energy with such a system, you have to work at a very high rate. This would never become a viable source of energy unless you work at a very high rate, because at a very high rate of working, the cost per kilowatt hour, if you convert it into an electrical unit, of the capital cost is low, whereas, of course, the recurrent cost of the fuel is relatively, is anyway low. So you have to, such a system, you have to work at a very high rate, and you have to see whether you can extrapolate, you can get to much higher power densities, and it's the power density you really have to increase. Now, as the research progressed, it turned out that people had other difficulties in conducting this experiment. And I think one point one must make is that although this system is simple to set up, it is actually quite complicated. We cannot control a great deal about the system. We can control the temperature of, at which we make the measurement, and we can control the current into the electrode or the voltage we apply to the cell. But actually, there are many other variables at stake, and we cannot disentangle the unknown variables. So this means you have to do a large number of experiments, and also, of course, experiments have to be done under unusual conditions. And I think that a further point one should make at the outset is you have to have a satisfactory electrode material. It's very easy to find palladium or palladium-like electrodes which do not generate any excess heat. Now, one very important point which I think one should make is that another reason why people found this very difficult to reproduce is that although under many conditions, if you start this experiment the experiment is entirely normal. In other words, you have again this relaxation coming to a flat top, and if you remove the calibration, this is the voltage applied to the cell. The top is the temperature, relaxes back to equilibrium. As you progress with the experiment, you find that this is not so. And what you find, in fact, is that you do, if you perturb the temperature of the system, it does not come to equilibrium. And when you remove the perturbation, the system does not relax to the point where it came from. Now, this particular effect is a manifestation of what is called positive feedback. The harder you drive it, the faster it goes. And it remembers that it went faster here, so there's a memory effect. So you have a system which has positive feedback and a memory. Now, if you don't know this, you will simply say, what will you say? Well, it's very obvious what you will say. You will say, the system doesn't work, you see. So you have to do sufficient experiments and sufficient blank experiments, and people did not do the blank experiments. You have to do sufficient blank experiments to convince yourself that you can make the measurement, and then you can take the effects of positive feedback into account. Well, if you do that, you find that eventually you can drive the system to the boiling point. So this is on a much smaller scale. Here are the calibrations. You start the experiment, and this is 9. A little bit? Okay. This is time. This is the cell temperature. This is the excess heat. Initially, it's polarized in a rather mild way, and then the polarization is increased, the current is increased, and you cannot see the details of the positive feedback, but I can tell you they are there. And when you see the positive feedback, if necessary, you increase the current to drive this thing up to the boiling point. If you don't do that, if you sit around the point where you see the evidence of positive feedback, the usual thing is you destroy the experiment. So, of course, I think what you have is many people, although they might have got to the point of seeing the effect, eventually they just destroyed the experiment. So this interested us greatly, and what we found, in a certain sense serendipitously, was that if we looked at the last day of the boiling cell, we saw that eventually the cell would boil dry. What do we mean? It's not really boiling. Eventually the cell would become dry. By this we mean that all the electrolyte in here, all the heavy water in here was evaporated. And what was so surprising about this was that we could make a video recording of this. We could see where the cell was half full. We could then see where the cell was full. So we could just say, well, how much heat have we had to put in to allow for the heat coming out through the walls and to evaporate the heavy water? And what we found was that we were had to put about 4 kilowatts per cubic centimeter into, generate about 4 kilowatts per cubic centimeter to explain our results. What happened at that time is people said, you have great, I beg your pardon, let me stop here. What we also found eventually was that the electrode stayed hot. After the cell had boiled dry and the current had cut off, the electrode stayed hot. And we were getting about 3 hours when the electrode would stay hot. Now, I don't think one can attribute too much to the temperature readings in here, because the temperature sensors which we had were not calibrated to operate at that point. And people said, Stan and Martin have great difficulty in explaining this. I have no difficulty in explaining it. It just, if the thing is driven on and it continues, it stays hot. And this was, we called this heat after death. We said that the cell was dead here, heat after death. Some other people said, no, the cell is live here, we'll call it heat after life. And a group in Italy, which I respect highly, called this after effect. This is an after effect.
It can only be from the nuclear reactor.
Well, if you estimate how much energy comes out of the system all the way through, I mean, this is generating gigajoules per one mole of material, and there's no way, in the end, you have about 1,000 times the energy coming out of the system, which I'm just doing this off the top of my head, but this is of the order of 1,000 times the energy which you can get out of any conceivable chemical reaction in the system. Now, I think one point I should one point which I should make here is that this group in Italy, which I respect very highly, has said, well, our own research group has shown that it is much easier to maintain heat production at elevated temperatures. And what they did is to devise a system which takes the heat out at a temperature close to the boiling point of the electrolyte. And what they found here is that when the cell had been boiled dry, they have been able to maintain this excess power. This is not specific, so it's about 5 watts per cubic centimeter for about 7 days. Now, 5 watts per cubic centimeter is not something which would lead to a significant large-scale device. It would be interesting for certain specialized applications, but it would certainly not be a significant means of generating energy. We have had energy releases up to about 200 watts per cubic centimeter under these conditions, but this has not, I should emphasize that this particular type of approach has not been adequately researched to make it into a viable energy source. To make a viable energy source, you really have to go back to the way we investigated it, to say, can we in fact maintain this, that's the wrong one, can we maintain the level of this energy production for a prolonged period of time? Now, I think I have to be totally honest here and objective. We spent a great deal of time trying to do this, and I'll just show you how this was done. You actually have to make a device which is like our temperature measurement at lower temperatures, and then when the system boils, you have to maintain boiling conditions for a prolonged period of time. Now, that is actually quite difficult to do because the system is inflexible. If you satisfy the need to do this, then it is difficult to satisfy the need to do that, and you have to just tune the system so that you can make the measurement. But in the end, we were able to maintain boiling conditions for the order of 50 days at an excess of, the excess energy production was about 80 to 100 watts in this particular system, like a reasonably powerful electric light bulb, and the energy density was about a kilowatt per cubic centimeter. Now, that begins to be rather interesting, because at a kilowatt per cubic centimeter, this is the cost. The costing seems reasonable, and also if you increased the production of palladium in the world, if you continue to do this with palladium, if you increase the production of palladium by a factor of 10, you would be able to satisfy a very significant part of the world's energy needs in that way, by that type of device. However, I must tell you that being an electrochemist, electrochemists, there are two, if you take separate electrochemists from the body of the scientific population, the main body of the scientific population says electrochemistry is a weird and wonderful means, and you can do more or less anything you choose to by electrochemistry. And then there's another much smaller group, which is the electrochemists who say never. I will never do this electrochemically if I can possibly avoid it. The grass is always greener on the other side of the fence. So this takes us really to the present state. If you think about the future, you say, well, how would you do it? What is the next possible way? Well, would you use this wire technique? Because you want to increase the energy production. If you want to increase the energy production, the rate at which you work it, you have to use a thin wire, else you can't transport the heat away. You're tied by the engineering considerations. But if you use this type of system where you use the electric field to compress the deuterons, then you would expect, if this leads to an equivalent energy production, you would expect to be able to get more extreme conditions without using up heavy water. Just, deuterium might go in here and might come out there, but it's still cycling around. And that has been done by a research group in Italy. I have confidence in this because we've also done some work of that kind ourselves. And this group has been able to routinely achieve energy productions of the order of 10 kilowatts per cubic centimeter, and on occasion as much as 100 kilowatts per cubic centimeter. And the figure of merit of 10 kilowatts per cubic centimeter, which is of course enormous, it's much more than you get in a fast breeder reactor, is very important because it shows that you could actually satisfy a considerable proportion of the energy needs in our existing energy needs within the existing pattern of production of palladium in the world, which is about 100 tons per year. Now, one point which I should have mentioned in going along, going through this expose, is that what we have at the present time, and I think for the foreseeable time in the future, are systems which can produce heat at 100 degrees centigrade. Now, that means that as the systems now stand, we are looking at energy production, what is called low-grade heat, for the applications which require heat at a relatively low temperature. But I think it is worthwhile to bear in mind that more than half the world's energy production is used up at temperatures below 70 degrees centigrade. Boiling here is 100 degrees, so energy production, the consumption is at temperatures below 70 degrees centigrade. So there is a very large base load of needs which might conceivably be met in this way. And it's also relatively easy to think of ways in which the quality of the heat, that is the temperature at which the heat is produced, would be increased. There's several ways in this could be done relatively straightforward way. So what is so sad about the whole topic is that here it is. I mean, it is still a very rough and ready research topic. It has not been in any sense fully investigated. The question of the materials has not been solved, but one would think that with the information to hand, you would continue. I think I should make one final comment, is that when we go through investigating the variables of these types of systems, we don't do it to convince somebody else that we are right. This is something we cannot do. We cannot convince somebody else that we are right. We do it to convince ourselves that we should carry on. But of course, we do not carry on, we cannot carry on if the work is not funded. That is something which you have to see to. Thank you very much.
This has been a presentation of Lightworks Audio and Video Incorporated.
Fleischmann, question and answer segment.
Yes, I was curious. There's been so much controversy with regard to what has happened. And also, there was a period of time where you were working under the Japanese.
Mm-hmm.
And that, of course, also was cut off. And the question I would put to you is, what would you have done differently if you could look at things again now, 10 years after the fact and during the intermediate years, to have changed the situation?
Dr. Chubb says, what would we have done differently to change the situation? I think that's very difficult. I think that I should point out that we did this entirely secretly with our own money. I had contemplated starting this research myself in the 1970s. I didn't do so, and we started it because Stanley Pons had some similar thoughts, and there's always a critical mass to persuade yourself to do an experiment, which is two people. One person can never convince themselves, you know, I can't do this, I can't do this. Two people, however, are the critical mass, and this led to us starting. However, we had to do it secretly. I had thought of doing it, and I rejected doing it while I was a permanent academic. I thought I could not do this research until I had retired, because I was under no illusion that it would be badly received. I think that in the end we got to a position when we had to inform the Department of Energy of what we were doing, and we also had to inform I had to inform the United Kingdom Atomic Energy Authority. There are these laws, you know, there are the US Atomic Energy Act and the UK Atomic Energy Act, that you have to inform them. We came to the conclusion in the summer of 1988 that we would need $600,000 to resolve the questions which we could see had to be resolved by September 1990. Now, that I think was unfortunate. I persuaded my colleague Stanley Pons that we should combine informing the Department of Energy with an application for funds, that we could save ourselves a lot of effort. In any case, we would have run out of money. We were prepared to spend $100,000 ourselves, but we didn't have $700,000. But no way. So we informed the Department of Energy. So this became enmeshed in a peer review of a research proposal, and that was unfortunate, because that led to all manner of problems which have been documented. The other point, I think, was that I really was I did not know whether the project should be classified. My main reason for thinking it should be classified was to obtain a period of quiet. I thought that this system had to be investigated calmly, quietly. Now, the way, by applying, because we had applied for research funds, it was impossible to maintain, unless this project was classified, it was impossible to achieve that condition. If we had been able to get to September 1990, I think I would definitely have recommended classification for a limited period of time of the project. Again, to ensure that the next step, the next phase of the work could be done in a calm way. Now, if the project had been classified, I think, and we had remained part of the group responsible for developing it, I think we would have been able to initiate proper discussion, scientific discussion. But the way it came out, with this polarization of opinion, you could not have a scientific discussion. You know, you had to produce all the scientific know-how by communicating with yourself, which is not a good way of doing it, because you know, we are not, we cannot combine all the virtues in ourselves. So that was unfortunate. However, I do believe that given the situation we found ourselves in, the project was bound to take the route it did. It was going to be driven into the open by the Department of Energy. We therefore had to tell the university what we were doing. The university was obliged to consider the intellectual property. People say this was a bad move, but I say, well, what would people have said if they had not taken patent protection? It's just not possible to conceive of a situation that they would not have done so. And then the patent became the dominant driving force, and the events subsequently, of course, were dictated by the patent, which was unfortunate. But I don't know what one could do to circumvent this, apart from classification. But I did not know how. You know, we had to pose the problem to the Department of Energy, should it be classified?
Regarding patent problems that occurred with cold fusion, I used to work at the patent office, and I have viewed the reluctance of the office to evaluate cold fusion applications on the same grounds as they do other types of applications. There is a lot of resistance within the office to issue any cold fusion patent. Do you have any thoughts about it and reasons why you might say that's true?
I hope the question is why has there been the reluctance of the patent office to issue cold fusion patents? Now, I'm afraid I'm going to be rather offensive here. I think the United States Patent Office serves the national interest. I think from a European, in the US, the view is projected that we cannot deal with countries which do not have the same attitude to intellectual property as the United States. I think we might find that in the future people will exclude the United States, because the way the United States treats intellectual property is not really acceptable to other people. And I would say that viewing it, I was not in favor of the patent. I think that this is not the sort of field which you can patent. As people have said, you can't patent this.
But then what does that say about the national interest?
Well, let's come to this slowly. What does it say about the national interest? I think we should approach this in a slow way. The United, well, I think that to me, it seems that the judgment made always in the United States, this is in the national interest. They would deny that, but I mean, I think this is pretty clear that this is the view. This is the view. This is how it proceeds. It is not evaluated. Matters are not evaluated on their own merit. They are evaluated with all manner of other considerations. Well, it's okay, you know, if they want to do it that way. Well, what is the national interest? That's for you to decide. I think the national, I can only tell you what I said at the time, that if this topic came into the public domain, industry would not wish to fund it. They might say initially, this is very interesting, but eventually they would withdraw because it's a very vulnerable type of research. You can imagine that you invest $100 million on getting a product, and next year somebody in a garage somewhere comes out with a better product, and your $100 million is down the tube. So it could only be as a licensing technology. So I did not see that industry would see it in the national interest. I did not see that those concerned with national economics would view it as being in the national interest, because the bottom line when you consider national economics is to leave everything unchanged. You only change things when you must. It's the old Boston learning curve. It's the Boston learning curve applied to energy. At some stage you have to make a change, but you don't make the change till you have to. I thought that those concerned with defense would not view it as being desirable, not because there was necessarily any defense application, but the attitude would be, we don't want, can we conceive that we want people in the university sector to research something which is concerned with nuclear processes? And the answer had to be no, I think. I think any reasonable view is that the Department of Energy would have taken a negative view of that. And I think this is the way the thing panned out. It was predictable. And I also thought that the project would be judged in terms of quantum mechanics and not quantum electrodynamics, and it would therefore be very easy to polarize people's opinion that this was impossible. Simplified quantum mechanics. I think Dr. Chubb wants me to say that quantum electrodynamics is a more sophisticated way. Quantum field theory. I stand corrected. Quantum field theory is a more sophisticated version of quantum mechanics, which of course is true historically, although I would say that quantum field theory should really precede quantum mechanics. We do not agree. We have two different views here.
Dr. Fleischmann, what are the technological hurdles that need to be overcome in order for cold fusion to become useful as a supplement to our world's energy needs?
The question is, what technological hurdles have to be overcome? Very difficult to say. I think the main hurdle is to make satisfactory materials which work every time and work for a long time. Now, we know that we have been able sometimes to maintain energy production at relatively high levels for long times, but 50 days is not something which would necessarily be acceptable. I think usually you have, when you construct an apparatus, 6 months is the bench line. Below 6 months, you don't do it. So you have to have a system which survives for 6 months, and we do not know yet whether this is possible. And what often happens in any development which is taken towards a stage of technology, is you find some very stupid hurdle which you cannot get over. You know, most processes fail. You know, somebody goes into the laboratory, has a bright idea, everything looks good, and you just cannot implement it. This is a very common pattern. I can't think that there will be any insurmountable obstacle as we now stand. I don't see this. I don't think there's an insurmountable obstacle, but then we may find that there is. I think you absolutely cannot say that this is fails, you know, this project will succeed. You can't say that.
Well, standard nuclear fission, nuclear power plants typically go between 12 and 18 months before needing to be refueled.
Mm-hmm.
So
but then you have the benchmark.
So if you use that as sort of a baseline,
Mm-hmm.
you need to have some sort of a fuel process that could last 12 to 18 months, perhaps.
I don't think the point is made that you'd have to have a fuel process which lasts for 18 months. I don't think this is true in this particular case because the reprocessing costs are very low. I think you would tolerate a much shorter time, and you could make a system where you insert the cathodes, and charging them doesn't take that long. You know, it takes a day to charge them. So what's a day out of 6 months?
In the context of the materials problem and the possibility, you pointed out that you can run into hurdles and problems.
Mm-hmm.
You also made the comment about critical mass, the need to achieve critical mass in order to decide on doing something.
Mm-hmm.
An interesting question, which I think is a very appropriate question, is what would be the mix, that is, the collection of scientists and their discipline in an optimal environment in order to overcome these obstacles?
The question is, what is the optimum mix of people to overcome the hurdles? Well,
And also
facilitate. I do not like working with large research groups, but I would have no difficulty in specifying the first 100 or 200 research projects which should be carried out. And I have always...
I hope you would share that with us so we can put that.
But it also, I mean, a related question. I mean, I agree with you about the research projects and so forth. But the mix, I mean...
now, okay,
also
the
be
mix of
industry,
scientists.
It could be the scientists, the industry. What would make it work?
Okay, all right, the mix. I think, continuing the line of 100 to 200 scientists, I have always maintained it needs Manhattan 2. To really get it to work, you need to have, it's a will, you have to have a statement, we are going to do it, and this is what we are going to do. You know? And if the society has evolved to a point where it does nothing, let me just tell you that I view our society in Britain as somewhere someone has made a decision that Britain should be a super Belgium. With this, I'm able to offend both the Belgians and the British. We are going to copy people. We are not going to innovate in Britain. The view is, something like 70% of all technological development since the war has been carried out in Britain or in America, the basic research. But we have not implemented, we have not had the benefit of this. And the view is that if we do less science, we will do more technology. I think we'll just do less science. Yes, but we will simply do less science because we haven't got a structure which allows us to use other people's. And whose technology, pray, are we going to use? Now, what is the mix of people? I think the unfortunate part here is what was really needed is a phase of university research, diverse university research, to establish the basis, the basic knowledge. And there is some very interesting basic knowledge which I haven't had time to present, like the production of helium-4 related to heat, like the fact that the hot fusion is wrong. The work in Japan which shows that really hot fusion is quite different to the way people imagine it to be. There are other processes. The processes which have been found are certainly there, but there are other processes, and the rate at which these processes take place is much higher than was thought.
Could you show that graph? The one with the 4 different nuclear processes?
I think I have it somewhere. The 4.
I actually saw it. Yeah, it was about
It's
5
here.
years below, about middle way. That's how you go by.
Oh, you are much more observant than I am.
They made copies, too.
Now, I'm sorry that this is a very bad slide because it is done with a pen on a piece of paper.
You're getting to it. You're getting to it.
It's done with a pen on a piece of paper on an acetate which does not accept the pen.
But at least it addresses the traditional nuclear reaction.
Okay. Let me just take this over here. And while I sort this through, let me tell you something else.
We can find it.
Let us find
I will find it. Dr. Chubb says, what mix of scientists should we have? The answer to this is, if we don't have the 200 scientists in Manhattan 2, or the 2,000 scientists in Manhattan 2, I would like, knowing, since I have worked with, in the United Kingdom system, I said, give me 6 United Kingdom physical chemists. And if I can't,
Solid state physicist.
no, I'm sorry to tread on your feet, and failing that, give me 6 from the Antipodes. With other words, this is only a personal preference. I have worked with people who've been trained in the British scientific tradition, and I know how to get them to work, which is basically get a whip out and make them work. You know, the British scientific there are 3 scientific traditions in the world: the British, the American, and everybody else. The British is a crazy system where we make people work at a very young age when they really are pretty ignorant, but they do seem to produce the goods.
There we go. There we go.
The American system is marvelous, fantastic if you have a lot of money. However, the American system, this is something you really have to watch. The American system is not good when funds are tight, because it's very wasteful. Okay, this is the brilliant slide. I'm not, and please, the smudge is, this has to be replaced.
We've got it on PowerPoint. We'll replace that slide.
Okay, well, put this one in and say you're going to do it better. The first, these are the traditional hot fusion reactions, about equal rates. You form hydrogen and tritium, neutron and helium-3. This one here also is reckoned to take place. That is, two deuteriums to form helium-4 and a gamma ray. A gamma ray is a very energetic photon, a light, you can't really describe it as a light. It's as though a light beam, immense energy. Now it,
50%.
and this is about 1,000th of a percent.
The first 2 have been observed inductively.
Yes.
It's inductive reasoning that predicts 50%. Any other?
Oh, no, this is known. This is now known.
By what reason?
By measurement. You measure helium-3 and you measure neutrons. You measure these quantities. These are quite easy to measure.
But my question is the branching ratio. Is the 50% predicted by theory?
You would predict it by theory, and you observe it by theory. Now, we were criticized and said you cannot get helium-4 because you have no gamma rays. Now, this is absolutely absurd, of course, because to get a gamma ray, you're producing a photon, and to produce a photon, you have to polarize the vacuum. And it is very difficult to polarize the vacuum.
What does that mean? I'm not sure what polarized. Well, wait.
Dr. Chubb is going to answer that because I can't think of an easy way of answering it.
Well, you can view it in a number of ways. The simplest way to view it is you have to have energy momentum conservation. And what happens is when you go to the center of mass location of where the deuterons combine, they have zero momentum. The center of mass, zero momentum, but there's all this energy around.
Yeah.
So they
That's
have
not
to be
going to
hitting,
happen.
They have to be hitting something. Now, polarizing the vacuum is one way of describing it.
The other way
Another way of describing it, which is equivalent, is to say the charges all rearrange themselves through a more complicated process.
What you have
as if
to-
they're colliding off the vacuum, and then that comes off the gamma.
You could say you have 48, you'd have to have 48 electron-positron pairs. A positron is like an electron, only a positive charge.
Another way of viewing it, yeah.
You have 48. Now, the chances of making 48 pairs, you know, this just doesn't happen in nature very easily. Now comes the big thing. When you do it in a lattice, it's, of course, much easier to polarize the lattice. And it's that simple. So when we had a different, I must say we had seen helium-4 before the dreaded press conference, but it was not publishable because our technique, this was really an example of you've seen helium-4, so you carry on. It is not something you could publish. In fact, some of the things in our paper should never have been said.
If I may interject one other additional comment. The first two reactions assume that the nuclear behavior is occurring on a very different length scale than the electromagnetic behavior. And for that reason, the helium-3 and the tritium, the protons and neutrons are essentially indistinguishable from each other. And that's
Hence
why they
50%.
occur with equal ratio. And that's the basis of it. The last reaction is electromagnetic in nature. Now, people have been assuming that it's dynamical, too, which is what you have when you polarize the vacuum, the way he's saying. But in a solid, you can have an electrostatic potential. Electrostatic potential does penetrate to all length scales and can provide a vehicle for momentum transfer. And that's a basic difference.
Okay.
So you would expect that one.
Now let me
My analogy,
come with another slide.
my analogy is that it's just a rearranging of clumping.
Yes, well, in the vacuum,
But it can happen statically in a solid.
and
In
now,
other words, that's the key.
now here comes the point.
Before we move that, the one point I thought.
Now I'm going to bring it back again to explain this.
When you bring it back.
When Lord Rutherford discovered the two reactions I've just managed to wipe out, although he really only found the top line, he said, having got the top line, we must have the bottom line as well. And he was right. He was always right.
Fission would never work.
Now, what?
Didn't Rutherford say fission would never work?
Rutherford said,
Was that Rutherford?
Dr. Chubb makes a comment that Rutherford
Wasn't
said
that
fission.
Rutherford who said that?
No, I think someone said, people have said to me, why did Lord Rutherford turn against nuclear fission as an energy source?
I thought he said it would never work.
No, he turned against nuclear fission as an energy source. I think my own feeling is that Lord Rutherford turned against fission as an energy source because by 1938, not 1939, by 1938, everybody knew there'd be a bomb.
Oh, maybe.
You know, the chemists had sorted out chain reactions. I know of two people who'd thought of the bomb before, two sets of people who thought of bomb before, and he was late. The British were working on it when Einstein wrote it. The French were working on it. The Germans were working on it. It was late on the scene. The Americans were not working on it. And Einstein said, Mr. President, what are you doing?
Messing up.
Here comes Dr. Fleischmann saying the same thing. Mr. President, what are you doing?
He's deaf. So what was wrong in 1934 was that when Philip D. measured the tracks of the proton and the tritium is a proton with 2 neutrons, they came out at 180 degrees. Most of them came out at about 160 degrees, which is what they should do, but a significant number came out at 180 degrees. So what Dee said in 1934 was these are the fusions of deuterons which have lost their energy in the target. Well, I mean, whether you say it that way or say it's cold fusion, I don't know. It's the same thing, isn't it? So there is a complication. There is a complication in the hot fusion. And the recent work in Japan has shown that this channel here, deuteron plus deuteron going to tritium and helium-3, is about 1%. No, beg your pardon, 10 to the minus 2%. This is all percentage. 10 to the minus 2%. This is percentage. But this is still a lot. You know, it's been thought that these are the only ones with possibly this, and now this turns up. And of course, there are other channels you would think of, other ways you would think of, you just haven't looked for them.
Right. But the concern I have is the first two are predicted to be 50%, and cold fusion's been criticized for not showing that 50% distribution, for violating the branching.
But look at
It's garbage.
Back up for a second.
Yeah, I beg your
All the
pardon.
reactions. None of them have high energy. All of them have high energy particles. There are no high energy particles involved in the dominant reaction. None.
That's a good point.
And so none of it really makes sense. Now the bottom one
Why would you get more tritium out than?
Well, what is remarkable, that should be totally impossible.
Yeah,
You know, if you think, when you talk about the energy release in the sun, the beta cycle, and you involve beryllium-8 or something, and the reason it is thought that this can be involved in the sun is because beryllium-8, I'm really talking off the top of my head, has a lifetime of about 10 to the minus 16 seconds. So a reaction to form beryllium-8 and then a further reaction of beryllium-8, just two species all the way, that is adequate to explain what happens in the sun. But now this thing, which is still, you have to call it warm fusion, it's not cold fusion, warm fusion. We're going down in the energy scale, and suddenly we see three-body reaction. Now, when you go still further down in the energy scale, you'll see a multi-body reaction. You know? So I think in the end you'll see the whole range, you know, it'll all pan out, but you won't find it if you don't spend the money.
Yeah, you see now a point there is if you get many, many particles coherently taking away the momentum, then you get no high energy particles. And that's why, you know, you can think of the helium, you know, the helium-4 can actually occur that way.
If this is in a macroscopic quantum system, a very simplified way would be to say, well, you can take all the energy away. So now, you see, I was not surprised by what we found, but everybody else was. It appeared as though everybody else was surprised. I don't think there were.
I mean, wasn't there a lot of confusion, right? Nobody knew exactly what was going on.
Oh, we said what we had seen.
Right.
I didn't say we had done this because I was interested in the quantum electrodynamic paradigm. If I'd said that, I mean, it would have been impossible. You know, you can't. In the 1960s, when I thought of doing various experiments to demonstrate the applicability of the quantum field theoretic approach, I thought I had various discussions at that time, and I was absolutely convinced that you couldn't say, I'm going to investigate quantum field theory in condensed matter systems. Supposing I had written an application, my standing was still reasonably high, both in the United States and the United Kingdom, and said, I'm going to investigate the implications of quantum field theory. Ha, ha, ha. No future in that at all, in my opinion. You had to do the experiment and say, here's the experiment, how do you interpret it? You see, there is a very important point here. When the quantum theory came on the scene, it was realized that the classical mechanics was insufficient. So we had to make a step. So although there was a lot of opposition to the quantum theory, it was not violent. You know? Even so, Planck, who was the originator of all this, said that progress in science takes place by funerals. You know, he had plenty of problems himself with that. I mean, you can't conceive what problems there would have been if we had put the paradigm ahead of the research. I'm content to talk about it now because I just can't continue with it, to just put the records straight. But I couldn't have put the paradigm ahead of the results. So I must confess that the paper everybody saw was written in an afternoon. You know, the pressure on us was so severe, we could not agree to the press conference unless we had a paper accepted for publication. Now, it could be argued that that paper should not have been accepted for publication. That's something which is out of our hands. But we submitted two papers and pulled one, and that paper was submitted for publication. And I must say, we never saw the page proofs because that's the way the cookie crumbled there.
If you had to do it again, would you have allowed the draft to have been faxed worldwide?
Would we have allowed the draft to have been faxed? We had no control. The reason.
The draft, you submitted it initially to Nature, right?
Well, I mean, it's the referees, or some of the referees, or the editor who faxed it around
Is that
the
right?
world.
You didn't.
I didn't fax
They
anything.
didn't, so somebody else did.
I didn't fax anything around the world. There is a sociological comment here that this particular announcement coincided with a widespread use of the fax.
Right?
And whenever you have a new publication medium, you have a phase of hysteria. And the first well-documented case of hysteria is printing. As people say, when the people in Amsterdam saw that they had the same problems as the people in London, then you got political unrest. I maintain that you would not have been able to have fascism without radio. And I think that the unrest in the late 60s was due to television, and this hysterical reaction, which was a localized reaction, was because only the scientists had faxes, really, let's face it, dominantly, was due to the fax. If there had been no fax, this would have not happened,
And
obviously.
Now we're having the hysteria due to the internet.
The internet, well, I mean, that is, the internet is something which is totally out of control.
Now, Dr. Fleischmann, I would like to get your comments on the alleged misconduct caused by MIT in 1989. The research that you had done with Dr. Pons was cited as false by a jihad, perhaps, of a number of scientists at MIT. Has the record ever been set straight? Do you feel that you were slighted for alleged misconduct, and has that record ever been
Well, I mean, people have written about it. There were 4 papers in 1989, which causes a lot of difficulty. I know that paper. Yes, I mean, people have commented on, especially the editor of Infinite Energy has commented, because he was the press officer at MIT at the time, so he should know what went on. I can't comment on this because I wasn't privy to this information. But as far as I can tell, the group at MIT said it was impossible, had a party to celebrate the fact that it was all nonsense, then looked at the results and found that they had got excess heat. Now that is a severe embarrassment. I think there's another research group in the United States where you cannot be sure what happened, but it is much more reasonable to interpret the results in terms of generation of excess heat than nothing. And of course, I was concerned with a group in the United Kingdom who certainly observed the generation of excess heat. But the comment I would make there is negative results which are wrong are never withdrawn. There's nothing you can do about it. I do not know of any case where a negative, it just is submerged in the negative critique. Negative criticisms are not withdrawn. Positive papers are sometimes withdrawn if the authors feel they were not right. And that's quite right too. Negative papers are never withdrawn. I don't think I've answered your question.
Unless it is proven, unless it can be proven that there was either a deliberate attempt to mislead, or that that there was an approved case of intending to show fraud.
Well, you see, you can have fraud in minor branches of science, but I don't think, honestly, fraud in anybody would set out to commit a fraud on fusion. That is something which is so mind-bogglingly stupid.
Oh, absolutely.
That I just can't conceive of that. But because of this attitude, I have actually used other people's results in my presentation.
Yes.
I've only used, I think, 2 or 3 results from our own work. Everything else has been from other people's work, because I don't want to use our own work. And I've got some more stuff here, other people's work, which I've evaluated. Here's a case study of another experiment done by another scientist in another laboratory, not his own. And I think all you can do is to do a set of case studies, and this is my interpretation. Here are the raw data. Now, this is another very important point. Raw data must be archived. The sociology of science is that when you do a new piece of work, either the negative conclusions are correct, or the positive conclusions are correct. But that is insufficient. The negative conclusions or the positive conclusions may be changed by a different interpretation. So I think the important point is to say, here are the results. This is what I conclude, and somebody else might conclude something else. And this can lead to a reasoned debate on which interpretation we should accept. Yes?
Who do you consider doing the most advanced work in Europe and Japan?
Who is doing the most advanced work? Well, there's a lot of very good work. I mean, in the United States, the group at Stanford SRI has done very good work, continues to do good work. I have a great admiration for the work done by Dr. Melvin Miles at China Lake, who's done this correlation of helium-4 with heat production. In Europe, I mean, I've cited the work of Dr. Mengele in Padua. I did not name the other Italian research group, which is led by Professor Giuliano Preparata, and that work is now being done in the Nuclear Research Institute in Frascati. And there's some splendid work in Frascati. There is, in Japan, I've mentioned the work of Dr. Takahashi. I think the 3-body reaction is very significant. Professor Kasagi has very interesting work showing that this is not really quite right when you use low energies. You know, the rates at which these reactions go, the absolute rates, not the ratio, but the rates, are much bigger than you think from doing the experiment at very high energies. So there is a very significant amount of work. I mean, bearing in mind how little money there has been spent, it's absolutely astonishing.
What about Professor Yoshiaki Arata?
Oh, Arata, yes, Professor Arata in Osaka University has done splendid work on heat generation and also the detection of helium-4. But what is especially significant about Professor Arata's work is he's also found helium-3. Now, when you look, we've always, the contamination, when people see helium-4, there's about 5 parts per million of helium-4 in the atmosphere. And if you imagine this leaking into an apparatus, you'd have to have a very big generation of heat to get beyond 5 parts per million of helium-4. But what is very significant is the ratio of helium-4 to helium-3 in the atmosphere is known, and what Professor Arata has found that under certain conditions, he has much more helium-3 than corresponds to the atmospheric in the atmosphere. And this has now been extensively confirmed by other people.
It raises the question, too, though, about the lack of detection of neutrons. Isn't it true that the neutrons really don't have enough energy to escape?
There are some neutrons. There are if you establish
Proton deuteron.
it's the PD reaction. It's not that reaction there. It's a proton deuteron, probably a proton deuteron reaction.
He's got a lot of regulated hydrogen in his apparatus.
I think what you get as you get neutrons and tritium here. Neutrons and tritium, as you establish the system, what is called a non-steady state. When it's going in a steady state, you get helium-4. But you do get, in a non-steady state, you get neutrons. You get very few neutrons and not terribly much tritium in the non-steady state, but you get even less in the steady state. But of course, you see, here I'd say people have never asked me, how would you make tritium? If they'd asked me that, I would have told them. They haven't asked me that. Well, obviously you have to do it with a sequence of non-steady states. Obviously. You don't have to be a genius to come up with that solution.
So in other words, if the criticism is that fusion is not taking place because the ratios are incorrect, you would explain that there are other considerations.
Well, the ratios aren't even correct for hot fusion. I mean, here is just one. The ratios aren't even correct for hot fusion. So why should they be correct for cold fusion?
I mean, well, the biggest thing is there simply aren't any high energy particles. Have you thought about the implications of magnetism and how magnetism might inspire or help catalyze?
We had a whole lot of thing on spin polarization, and God Almighty, the things we discussed. Yes, I'm sorry, I shouldn't say God Almighty. I think this will offend some of your potential listeners. You know, we could discuss all these things, but that's another part of the problem.
Your answer is yes?
Yes. Your answer is yes.
Well, I always explain to people I'm a very conservative scientist. The answer is maybe.
You hedge your bets.
No, there are some things I simply will not. You know, I have to explore all possible conventional explanations, but my explanations include quantum field theory. That is the difference between me and many other people. I'm prepared to encompass the whole range of present-day knowledge, not just to say that if it doesn't fit quantum mechanics, a very conventional, limited view of quantum mechanics, then everything else must be wrong. That I'm not prepared to say.
Dr. Fleischmann, this brings to mind another interesting question where we could possibly look at the interactions that are occurring at this level, possibly with, let's say, low-level gamma rays or low-level electrons with, or possibly electrostatic charges, or let's say, a small amount of neutron source. Has there been any research to see if the cold fusion effect is enhanced by adding any conventional
I think
interactions?
People have tried, but I don't think terribly well. You know, there are a few haphazard experiments, but I don't think they are of such a nature that you would put any great credence. So you would have no confidence in them, I think. You wouldn't have much confidence in many of the experiments which have been cited, both positive and negative. I think you have to be very cautious here. Of course, people have said, you know, people have done everything from invoking particles created in the Big Bang to, you know, black hole. You know, people, you get all these cranks writing to you, I'm an expert in magnetic monopoles. I think cold fusion is the ultimate example of the operation of magnetic monopoles, and I go and have another cup of coffee. Yes, please.
I know the case of scientists who consider this a worthwhile area to explore, but because of the stigma that they had to go entirely underground and be secret for fear of loss of their jobs and support of their families. And I wondered what you would say about a type of a smear or a fear campaign that just characterizes and labels this whole field as fringe and wacky and pseudoscience.
It's certainly so. That is the way it's gone.
Yes, it has.
And so how would you mount some type of education effort when this topic is so esoteric for the layperson, for the public?
It's very difficult. It's very difficult. I know, I mean, I have great sympathy with people who say, I cannot, you know, who might have worked on it and I can't work on it and I better say it's wrong because my career is at stake and, you know. What? There are some,
don't do that.
There are some people who are very noticeable who don't say that. But
I don't get promoted.
he just gets stuck. But the ultimate end product of this sort of conservative society is fascism. I'm sorry to have to tell you that, but this is always a terrible danger. Conformism leads to fascism, where that the policy is decided at the center. It isn't clear how it's decided at the center. There's some consensus, some horrible consensus, and everything in the end goes down the tube. I don't know how one can overcome that. You cannot expect. This field has lived by virtue of a number of old people, like myself, who say, I don't care about my reputation. To hell with my reputation. I'm going to do it. And if you think I'm a fool, then please think I'm a fool. But you can't expect that of young people. And it would have to be a very exceptional young person who would say, I'm going to put my career on the line. What's wrong, of course, is that his career is on the line. It should be, this should be, you should, it's the same thing as saying it's pathological science. I'm sure you've run across this. We are going to judge this field in terms of pathological science. The person who has worked in this field should not be judged by the work he has done in this field. He should be judged by the work he can do in the field for which he is an applicant. Now, that, I'm afraid, doesn't happen. Everybody is judged by the work they have done in the past. This is very unfortunate.
And what about bringing in politicians or some type of investigation, or looking at, in the case of the patent office, 200 patents that have been refused, and bringing that up for some type of.
Yeah, I think there has to be, at some point, there will have to be a judicial inquiry. That is the word I was searching for. I think there has to be a judicial inquiry. Not just about this, but about the whole operation of the science system. We, both in Britain and America, we are very fond of leaving people to their own devices. Here's a sum of money, you decide what you're going to do with it. Because we're really not competent to say. But then the problem is that the leaders of the field don't seem to be competent either, and are very biased. And there has to be maybe a judicial inquiry about the process of publication and the process of peer review and the whole process of funding. The real question, or the real point, of course, is you have to spend some real bucks to get it moving again.
In a similar vein, what you're suggesting sounds like a very, very difficult task.
A judicial review?
Well,
judges are extremely good at judicial reviews.
Well, no, that's true, but whether the judicial review, obviously it gets down to the question of political clout, and maybe that will work. Maybe that kind of process will work.
The judiciary is more independent of the executive than any other group of people.
That strikes me about this is it gets back to what you said about Planck, and what Planck said. They'll have to die before it's accepted. The funerals.
Oh, that will happen, but it may have.
And there's an interesting thing about this. I think that things have also, there are two forces. They'll have to die, and there's also the marketplace. And how things can be solved. The question I would put to you in this context is, well, there's the marketplace, there's the judicial, but there are also social entities that could also help. Possibly, I don't say this necessarily, but
they're too disorganized.
Churches or other venues, educational venues, schools.
I was going to.
And the question I would put to you is, what should be explored, and how,
everything.
And how might one explore it?
I was at some stage I contemplated, when we still thought we might get the patent, giving it to the Catholic Church, because originally I'm a lapsed Catholic, but I am a Catholic. I thought maybe the Jesuits can finish it off. They certainly have been very tough.
Well, seriously, okay, maybe things fail in this country. All right, you go to another country. You get things developed.
Well, it's not
the patent situation, for example.
It's
Suppose we
not.
apply for patents in Mexico. NAFTA makes patents in Mexico good here, right?
It's not desired in this country, so it'll happen in some other country. That is the way it'll go. And I only hope that people will not suddenly wake up one day and have a major regret.
I've got a question about the loading ratios. Back in the second International Cold Fusion Conference, that seemed to be a big discovery, to make loading ratio equal, 1 atom deuteron to a helium. Is that gone out of fashion?
Well, the loading ratio is a macroscopic measurement, and if you have fusion in some bit and nothing somewhere else, the loading ratio will never tell you that. So I thought this was a pretty thin. I don't think the loading ratio was really investigated. I think it is interesting scientifically, but I don't think the loading ratio was investigated because of the wish to further the topic.
Well, you're referring to what the Japanese did.
Well, I think I'd prefer to answer that question when the tape is finished.
What do you think would make the optimal geometric shape for a continuous cold fusion cell? Have you given any thoughts to any of the engineering issues?
Oh, all the time. We started off with large pieces, and we had an accident. This is very well known. We had an accident, at which time we stopped the research and instituted work on large sheets under very mild conditions, which we stopped again in March 1988, and then we instituted thin rods, because we wanted to scale down the phenomenon. We wanted to keep it absolutely safe. But I don't think rods are a good configuration, because there is a concentration of stress in the core. And both ourselves and other people feel, I think, that sheets would be a better configuration.
And what about high pressure?
Well, high pressure, if you wanted to get high temperature, it would increase the pressure. If you do this migration experiment, you might increase the pressure. But I think you could also generate steam and use steam compression. This is a well-established technique to produce a high quality heat. There are various options for increasing the performance, but I think that the one thing you've got to realize, you've got to get the heat away. There's a lot of heat, so you have to have a thermodynamic liquid. Well, what thermodynamic liquids have you got? You've got hydrogen, deuterium, helium, water, heavy water. You haven't got anything else. You have liquid alkali metals, as in a fast breeder, but I don't think anybody will follow that route in a hurry. Although I did sketch a design for running a system with a liquid alkali metal to get the heat. Well, that's steam. You would run with gas in the Stirling engine or with steam. And that's low. I'm attracted to using low technology, 19th century technology. I'm not attracted to 20th century technology. I always go back and say, how did they do it in the 19th century? That'll have to be good enough for us for the time being.
With regard to his comment about the loading, there wasn't a lot of emphasis towards getting like the one-to-one loading, but it's quite clear that in order to get into the regime where the effect, the beta phase regime, you have to get loadings that are, like certainly greater than 0.6 and really in the neighborhood of 0.8.
Oh, well, we knew that.
To go up as you
We
go
knew
up.
that.
You knew that, but with regard to what Tom was saying, part of the emphasis was just getting that fact out, and then subsequent to that, of course, the NITI-sponsored program went on and on and on, and when ad infinitum.
I think people have cooled off a lot about that.
Yeah. They weren't paying attention to the material.
I think we have to watch the time here, gentlemen.
Yeah. One last question. In the movie Chain Reaction, the illusion was that the high pressure, the various size of the experiment could cause an explosion. Could you address that?
No. All I would say is I have no evidence that this is so, but I have not researched it and I have no intention of researching it. And if you said, do you think you could have a runaway situation? I would have to say, well, I can certainly conceive of a runaway situation. I have no evidence, and being a very conservative scientist, I say maybe.
Sure, for some reason. Sure, for some reason.
I think it certainly has been a real privilege to have Martin Fleischmann come and talk to us. I think he summarized very nicely a number of important issues. In particular, the need for very precise measurements that were not known. One thing he did not emphasize was that the measurements that were taken involved very long periods of time. During the initial stages of what went on with cold fusion, people did not perform very careful experiments. He showed quite explicitly the need to achieve a feedback mechanism that was certainly not well known at the time. And in any case, I probably talked long enough. We certainly have touched on a number of very important issues. I think it's appropriate to just thank Martin Fleischmann very much for coming.